Hello, everybody. So now we are on the second lecture of the production of power from heat. But before that, let's review what we discussed so far. All right. Last time, before we started the discussion proper on the production of power from heat, I gave some general information. First, on the global energy demand, that it's increasing. So we need to increase the supply as well. But the problem is the energy source, energy source for power generation. And we discussed the various energy sources, beginning with fossil fuels. But we know that they are not good because they are the cause of global warming, then nuclear fusion. So there's a big development on this technology, but still it remains to be expensive. And then we discussed the renewable energy sources like the solar energy, wind energy, geothermal, electric, tidal, biomass. Then for biomass, um, we discussed that they can be converted to solid, liquid, and gaseous fuels. We also touched on the Philippine energy mix, and based on the data, we are still very reliant on coal and natural gas, which are fossil fuels. And also, we are still importing almost 50% of our energy source. The rest we produce ourselves, but we still rely on imported energy source. So, and that's quite sad. We hope um, to be self-reliant in the future. Then we started the formal discussion on the heat engine, which is an engine that pumps heat from a high temperature reservoir to a low temperature reservoir, and in the process produces a net amount of work. For the steam power plant, this is a heat engine wherein the working fluid is in steady state flow through these devices in a cyclic process. So this is a diagram of a steam power plant with the basic components. And we said that if we still want to use our power plants having this configuration, but we want it to be sustainable, then we must replace the fuel from fossil fuels to renewable sources of energy uh, in the boiler. So we simply have to retrofit the power plant so that the fuel source is renewable and sustainable. Next, we discuss a Carnot engine, which is a heat engine operating in a completely reversible manner. So this is a Carnot engine. On the TS diagram, temperature entropy diagram, we discuss the Carnot cycle, and as you can see, it's operating inside the saturated curve. Okay. And all of the steps are reversible. So what is the use of a Carnot cycle? So when we calculate for the efficiency of a Carnot cycle, we can use it as the basis or the ideal efficiency of of that engine. So remember, we cannot achieve that ideal efficiency. We can just approach it. It's the highest efficiency for that heat engine operating on that low temperature and high temperature. So next we discuss the Rankine cycle, which addresses the practical difficulties in a Carnot cycle. For example, um, the practical difficulties are the severe erosion problems because of the high moisture content in the turbine, as well as the design of a pump that can take a mix of liquid and vapor. So this is a very difficult pump to design. That's why the solution is superheating the vapor in the boiler before entering the turbine so that the quality of the vapor increases, and also subcooling the liquid, as it passes through the pump, before it passes through the pump. So as a result, the cycle on the TS diagram is changed to this one. So remember, for the Carnot cycle, it's just operating inside the saturated diagram. But now, as you can see, this is the curve for the boiler. There's a constant pressure heating wherein the fluid is superheated to point 2, and then as a result, it expands in the turbine with the higher resulting quality. So when we say higher quality, the vapor part of the vapor liquid mixture is higher. So there's less moisture, therefore less erosion problems for the boiler. Next, in order to address the pump that can just take a liquid inlet, we um we ensure that in the boiler, the condenser, the fluid is condensed to its saturated liquid state, and also there's a subcooling, meaning uh the fluid exits the saturated curve. So this is the subcooled region, and the pump can now handle our liquid. So there are still reversible steps here, uh, from points 2 to 3 and from points 4 to 1. But in reality, uh, it's not possible. So we are always going to a higher entropy state. That's why in reality, these lines are always leaning towards the right, or leaning towards a higher entropy. Okay? So it's not a straight vertical line, rather it's slanted to the right. So this is an actual Rankine cycle. Next, we did energy balances for all of the devices in the cycle, for the condenser, for the turbine. So these are the energy balances for each of the device. And of course, we have the energy balance for the pump. And then next, so this is the boiler and condenser combined, and then turbine, then pump. And then our next discussion is on the efficiency of the entire power plant. Efficiency of the entire power plant. So first, if there's negligible pump work, the efficiency is the network produced by the cycle divided by the heat absorbed in the boiler. So if there's no pump work, our equation simplifies to this one. However, if there's pump work, our equation um, becomes the one right here, because now we're considering the work required by the pump. Okay, and then so we're also given, or we we also need the efficiencies of the turbine and the efficiencies of the pump, which are calculated using these equations. For the turbine, since the ideal work done by the turbine is always higher than the actual work, then the ideal delta H, or change in enthalpy, is in the denominator. Okay, so this value is always less than 1, this ratio. But for the pump, so the pump requires work, while the turbine generates or produces work. So for the pump requiring the work, its ideal work required is always smaller than its actual work required. So that's why uh, the smaller value is on on the numerator. Okay, so memorize that. Then we discussed, okay, a sample problem. Let me share the sample problem. So remember, this is example 1, sample problem 1. Uh, and it's recommended that first you draw the cycle on the TS diagram to guide you on the state of each point. Okay, so for this problem, we're given the superheated properties as well as the efficiency of the turbine, and it was said that pump work is negligible. We're also given the actual work by the turbine. We required the mass of flowing stream and the heat released or heat dumped by the condenser. So actually the first step, so uh, uh, second to writing the or drawing the TS diagram and writing the given required is to do the energy balances. And to get the mass of flowing stream, we can actually use the equation, the energy balance for the turbine. Okay, so this is the energy balance for the turbine. We're already given WS, or the actual work done or produced by the turbine. We don't know the change in enthalpy. So that's our goal. And we can do that by solving the enthalpies at each step. So remember, um, step by step, we solve the enthalpy. However, we don't know we're stuck with delta H ideal, okay, since we are able to calculate delta H ideal from the uh, isentropic expansion of the turbine from point 2 to 3 prime. So we can make use of the efficiency of the turbine to calculate delta H actual. Okay? So that's what we did. And from there, we're able to calculate the mass of flowing stream. Next, for QH, we just simply use the energy balance equation around the condenser to calculate for QC. I meant QC, to calculate for QC. Okay, for example 2, so remember the next example, um, it's another Rankine cycle. We're given the superheated properties and exhaust properties. Okay, and we're also given the efficiency of both the turbine and the pump. So now the pump work is not negligible because we're given its efficiency. Again, we began the problem by drawing the TS diagram and then doing the um, equation. Since the efficiency of the entire cycle is required, so we use the equation for the efficiency. So this is the equation for the efficiency, and we're able to solve the problem by calculating for the the property of the enthalpy property at each point in the cycle. So after calculating the efficiency of the cycle, we compared um, the efficiency with that of a Carnot cycle operating at the same working pressures. And we're able to know that obviously the Carnot efficiency is higher. And we can interpret it as um, 27.76% of the heat absorbed in the boiler is converted to work, uh, and the rest is just the waste heat released in the condenser. Okay, so as you can imagine, it's such an inefficient process. So current power plants are still really inefficient. There's a lot of waste heat. So our goal is to increase the efficiency of our um, power plants, and we can do this by first superheating. Okay. Remember the efficiency of a Rankine cycle with negligible pump work. This is the equation for that. And this is the net work or work produced by the turbine, H3 minus H2. So to increase the efficiency, this numerator has to be increased. And we can do that by increasing the temperature of the superheated steam at constant pressure in the boiler. Okay, so to increase the difference of in the enthalpies. Okay. We have here an example, but I will show the calculation later. Okay. Another way, so before that, so those are the results. Um, because in the problem, we are going to calculate the efficiencies and quality at the different temperatures. Okay. And as you can see, the higher the temperature of the superheated steam, the higher the thermal efficiency, and also the higher the quality of the exhaust steam. But it would mean that there's a high cost for the boiler because uh, the materials used for the boiler should be able to withstand the high temperatures. Okay. So this is how an increase in the boiler temperature can is portrayed on the TS diagram. So from a low temperature to a higher temperature, as you can see, there's a increase in work net, which is this area right here. Another way to increase the efficiency is by um, increasing the working pressure in the boiler. So still we have this equation for the efficiency. We have to increase this the value of the numerator, and this can be done by increasing the working pressure. And as P increases, T also increases. We have a problem right here wherein we're being asked to solve for the thermal efficiency and the quality at different pressures. Okay, so the result would be this one. So as the higher the pressure of the superheated steam, the higher the thermal efficiency, but the quality of the exhaust steam decreases. Right? It entails high cost for the boiler since the boiler should be able to withstand the higher pressure of the working fluid. As well, it may cause erosion problems because of the low quality of the steam in the turbine. So this is how the increase in boiler pressure can be portrayed on the TS diagram. As you can see, this is the lower boiler pressure. Increasing it to this level would result to a decrease in quality. Okay, so we're nearer the saturated liquid curve and farther away from the saturated vapor curve. Okay, so we want to increase the efficiency of the cycle, but As the pressure in the boiler increases, T increases also to unsafe levels. Okay, and it entails higher costs for the boiler and superheater to withstand the pressure and temperature increase. And also, if we increase the boiler pressure, the quality of the exhaust steam decreases. Um, it increases the thermal efficiency, but increases the moisture content that will cause erosion problems. Therefore, practical or actual power plant seldom operates beyond 10,000 kilopascals and 600 degrees Celsius. Another type of Rankine cycle is the Rankine with superheat and reheat. So it modifies the basic Rankine cycle by reheating the partially expanded steam. So after partial expansion, the steam is withdrawn from the turbine and reheated at constant pressure. It's a practical solution to solve the excessive moisture problem in the turbine, and it's commonly used in modern steam power plants. So therefore, the turbine is made up of two stages, a high pressure and a low pressure stage. So this is how the superheat with reheat looks like. So the superheated vapor enters the turbine and at a lower pressure, and then it exits the turbine to be reheated in the boiler and enters the turbine again. So the turbine is divided to higher a low pressure turbine and a low pressure stage and a high pressure stage. So for the rest of the steps, it just follows the basic setup of a Rankine cycle. So C, okay. So baliktad pala. This is the high pressure step stage, and this is the low pressure stage. Mauuna yung the high pressure stage come first. See, this is the higher pressure, and then it exits the turbine to go back to the boiler for reheating, and this is the lower pressure stage. It's a lower pressure, this is the higher pressure. Remember that. So there's a correction. The first stage is the higher pressure stage, and the second stage is the lower. So it exits at the high pressure stage and to the boiler, and then is reheated, and then it exits the lower pressure uh stage. Okay, so we have an example. But before that, for the seat work, I would like to go back to the problem earlier. Okay, on the effect of superheating, on the efficiency. So what we'll do is I will demonstrate one temperature, okay, and you will solve the rest of the temperature by group or by pair. Okay, so let's answer this problem first. Uh, so we're given the operating pressures. So this is the inlet pressure at the turbine, and this is the outlet pressure, and this is the inlet temperature. So we're asked for the thermal efficiency. Okay, so let's solve the problem. Okay. Effect of superheating. So let's draw the TS diagram first. TS diagram. So oops. Imagine this is just a straight horizontal line right there. Okay. So this is point 1, point 2, point 3, point 4. And what we're given, um, steam at point 2 enters. So P2 is 3,300 kilopascals. And P3 is, so this is P3 is 50 kilopascals. Uh, Turbine enters. So we have three. So we have three temperatures that we have to solve. 450 degrees Celsius, 550 degrees Celsius, and 600 degrees Celsius. 650. 650 degrees Celsius. So let's try at 450 degrees Celsius. Okay. So we're being asked required the efficiency of the entire power plant. So the equation for the efficiency of the entire power plant, let's assume that there's negligible pump work. So remember, it's the net work net over uh, QH. Okay, or the heat absorbed by QH. This is QC. So the work net, if there's negligible pump work, it's what? H3, simply the work done by the turbine, H3 minus H2. Okay, so this is the turbine. So this is the isentropic H3 minus H2 over QH. So QH is the difference in enthalpy in the boiler. So H2 minus H1. Okay? H2 minus H1. So we need this, the properties. So let's, since point 2, we know already the pressure and the temperature at point 2. Okay? At, so P2 is 33 kPa, while T2 is 450 degrees Celsius from the steam tables. ST H2 is H2 is, what is H2? 3340. 3340.6 kilojoules per kilogram. And then S2 is 7.0373 kilojoules per kilogram. Okay? Then, so we know H2 already. What's at point 3, it's wet steam. Okay, point 3, wet steam. So, kanina it's superheated steam. Just put here superheated steam. So, at we don't know the properties here, but we know P3 is 50 kilopascals. That's given. And therefore, if it's saturated, automatically we can take the temperature from the steam table, 81.35 degrees Celsius. And we know the isentropic expansion is just equal to S2 equal to 7.73 kilojoules per kilogram. We can read uh, the properties of the entropy of the liquid and the vapor, and it's uh, 0.0 1.0912 kilojoules per kilogram Kelvin okay, and S3V is what is S3V 7.5947 kilojoules per kilogram. Okay. So we can calculate for X prime quality here in the isentropic expansion. Quality of the steam through isentropic expansion. What's the equation? So remember, it's just simply S3 prime equal to S S3L times 1 minus X prime, okay, plus S3V times prime X prime. So substituting the values, X prime is 0.9143. Do we have everything that we need? Wala pa. H3 prime lang. So, to calculate for H3 prime. Okay, there's an important information that I forgot. We should assume isentropic expansion because we're not given any efficiencies of the turbine and we're not given any actual work. So we should simply use the we should assume isentropic expansion. Okay, so let's write that here. No information, so assume isentropic. So if it's isentropic, H H3 prime, H3 is H3 prime kasi vertical line, and then H1 is H1 prime. Okay, it's a vertical line. Okay? And so, can calculate for H3 prime given from the steam table. So, from steam table, H3L is 340.564 and H3B is 2646. So H3 prime, so we simply use X prime for this one to calculate H3 prime. Plugging in these values, H3 prime is 2448.466 kilojoules per kilogram. Next, at point 4, saturated liquid. Okay, point 4, let's see, diba? It's saturated liquid at point 4. So what's the conditions? P4 is equal to P3. So P3 is this one and this is an isobar. So P4 equal to P3 is, what's the value? 50. It's given 50 kilopascals. So from the steam table, H4 is 340.564, the same as this one because the same pressure, and we're on the saturated liquid curve. And V4 is 1.030 cm cube per gram. Next, we check. So, meron time H4. So, let's go to 1, to point 1. So, subcooled liquid. It's outside. This is one is outside the saturation curve. Um, Subcooled liquid. What is P1? What is P1? How can we know P1? So remember, this is an isobar, so P1 equal to P2, P1 equal to P2, P2 equal to 33 kilopascals. Okay? So we make use of the work of the pump. The equation is, so isentropic, this one is isentropic work. Isentropic work is P1 minus V4 minus times P1 minus P4. Okay, so remember let's just energy balance. So plugging all of this, P1, we know P1, we know P4. So it's 0.001030, and that is uh what's the unit? Meter per meter cube per kilogram times 3,300 minus 50 kilopascals, kilonewton per meter squared, diba? Kilonewton per meter squared. So, the resulting one is kilonewton meters per kilogram. So, that's kilojoules per kilogram. And it's 3.3475 kilojoules per kilogram. Okay? Um, but Okay. So this one, I have a correction here. This one is from the energy balance. This is actually delta HS. Okay, this one is delta HS. Sorry about that, guys. Delta HS. Okay, this delta HS. Mm-hmm. So now, but delta HS is, ano bang ginagamit natin symbol? May parenthesis. But delta HS is H1 prime minus H4. Okay? So, we can calculate for H1 prime. H1 prime. Okay, kasi we have delta HS and H4. So, we're given those values. So, we we are able to solve for those values and then plugging into the equation, we can solve each one prime 343.9115 kilojoules per kilogram. So now that we have all of the information that we need for the efficiency, which is H3 prime minus H2 divided by H1 prime minus H2, H4 pala, H4, diba? H3 prime, H2 minus H1 prime pala. Sorry about ano nga pala, boiler. So, this is for the turbine, yung numerator, H3 prime minus H2. For the boiler, it's uh, H2 minus H1 prime. Right? The boiler. Yep, H2 minus H1 prime. So, substituting the values that we calculated, the efficiency, and multiplying it by 100%, the efficiency is 29.77%. Okay. Um, and let's go back to the problem. Yep, it's this one. So the quality, so we're able to solve the quality, point 0.9 something. Yep, 0.9143. And also, we also have to calculate pala work shaft and Q in. Q in here is just QH. So, ano ba yung work shaft? Remember, work shaft is just this one, the numerator. This is the work shaft. And this is QH or Q in equivalent. So, just plug in the values. H3 prime minus H2. Uh, and we will get, for work shaft, it's negative 892.1936. For QH, it's positive 2996.6885 kilojoules per kilogram. So let's see. Uh, yep. So these are the values. Okay, now it's your turn to solve for 550 degrees Celsius, 650 degrees Celsius, and also for the other groups, it's your turn to solve uh, the next problem. This one, 5,000, 5,000, 7,000, and 10,000. Okay? So now I will give you time to solve, to do the solution to complete this table.